In allowable stress design, the concept for achieving what we call safety margin or preserving structural redundancies is by the following expression. You can also find this from the steel design book, which is capital R sub n, that means your minimum strength, divided by the factor of safety. And this ratio must be greater than the summation of all your nominal working stress. So that is Q sub n sub I. And in this definition, capital Rn is what we call nominal stress, strength. Of the material, of course. And the capital Q and I is normal working stress. In other words, the margin of safety is achieved by reducing the nominal strength, because in this case, factor of safety here is usually greater than 1. So by reducing your nominal strength, we have preserved the safety margin of the structure. That's the concept in allowable stress design. Next one is called plastic design. In plastic design, the concept is this. R and P must be greater than or equal to gamma times the summation of all the nominal plastic strengths, which is Q sub Ni. In this case, R and P is, we call nominal plastic strength. And this coefficient, or this factor gamma, is what we call load factor. So in plastic design, margin of safety is achieved by amplifying the loading. Or in other words, by reducing the strength. Next one is load and resistance. Factor design, or we call it LRFD. You must have seen this from steel design, right? So how do we preserve the margin of safety in your design? Is by doing both. You reduce material strength by using this factor phi, and then you also amplify your loading. I equals 1 to m gamma I times Q and I. So here, phi is what we call resistance factor. And this resistance factor is usually less than 1. And your gamma I here is what we call load factor. And this load factor, gamma I, is usually greater than 1. So in LRFD, we have both. Whatever on the left-hand side is about material strength. So this is the design concept. This is material strength. And on the right-hand side, everything here is what we call external loading. This is the same thing with all other design philosophies. Now, if you look at this, another higher up level understanding of this is this. You can also consider external loading as well as your demand, or you can call it structural design demand. What about the one on the left? That's your design supply. So the whole concept between or among different design philosophies is basically to compare your supply and your demand. If you supply more, then you have more safety margin. If you reduce your design supply, of course you save money, but you have less safety margin. This is the way to look at these different design philosophies in this case. Okay, now we finished the introduction and we can move on to the topic I'd like to talk about schedule for tonight. I know that we may be a little bit late from the beginning, but don't worry about it. We will catch up very quickly. Any questions before I move to buckling of columns? Nope, good. Good. So let's go to buckling of columns. And in the buckling of columns, our focus is on the effect of boundary conditions. So we're going to start with the most simple structure system, which is just columns. So what defines a column? A column member is a member defined by the application of an axial force. So if the member is subjected to an axial force, that means that is considered as a column member. I know that one of the examples we talk about it tonight, or started with last week, I consider the beam column, but that's actually more difficult. And now we come back with the most simple case, that is buckling of columns. And we're going to use the force approach to analyze the buckling loads tonight. So we already talked about this example, right? The spring bar system without imperfection. So what is imperfection? Imperfection means when you design the structure, or when we analyze the structure, we know that in theory, we don't want any geometric imperfection in all the structures. However, realistically speaking, you know that's not true, right? And we have seen that despite the best effort invested by contractors, there will always be material imperfection and geometric imperfection in real structures, which is the case we can consider and model them here regarding the buckling load of these imperfect structures. And we're going to use different examples to consider that. And let me start with a spring bar system without imperfection. We already considered that. That's the one we just did before. Now let's consider the case with imperfection, which is, in this case, with the distributed moment. That is example 5, right?
Professor, can you just switch your screen?
Thank you very much. Thank you for your reminder. I got to remember this because we will be doing this constantly.
Professor, one question. Will you be posting your notes and lecture slides on Blackboard by any chance, or no?
I will. I have no problem sharing this with you because if I'm sharing the video with you, what's the point not sharing this result with you, right?
Right.
So the
Okay.
answer is definitely yes.
Great, thank you. It'll definitely help.
Okay. So now let's try to consider that if there's a spring bar system and with imperfection, that means what? That means unlike the structure that we considered before, now the spring bar system we want to consider has something like this. And it has a rotational spring, which is like the one we solved the problem before. The rotational spring is denoted by rotational spring constant Ks, just like what we did before. And the loading is applied at the top. That's what makes this member as a column member. And we also call that this point is A, this point is B. Of course, as usual, your total length is still L. And it also has the Young's modulus E and mass moment of inertia I. So EI, all these are the same. Now, the only thing different is we are going to introduce a internal moment. That means before the application of this force P, there's already an internal moment. And what does that mean? That means this is the case when there's no internal moment. But when there's an internal moment, do you think that that would change the configuration of this column or not? So my question is this. Before, we never consider any kind of imperfection. Now we're going to consider some type of imperfection, and we're going to model this imperfection by an internal moment. It's called M naught. Now my question is, when I introduce this moment, in this configuration, there's no internal moment. But when I introduce this moment, do you think that there will be some change of the configuration? Or do you think not? If the answer is, the question is yes or no.